Tomorrow we have the test. Any questions from the practice exam or homework? No? Good? All right, then we're going to talk today about the KSP double dagger. And KSP double dagger is for sulfides. Like that guy. So if you have something like copper sulfide solid, it would split up into copper ions and sulfide ions. Right? And there's a problem with sulfide, though. The problem with sulfide is a very powerful base. It's too strong to exist in water, and what that means is sulfide is automatically going to attack water. So when sulfide attacks water, the base plus water will act as the acid in this case. It's going to form HS minus plus OH minus. So it's a strong base, then we say K is very large for this particular process, the second step of this equation. And so that means all the sulfide will be converted into HS minus here, and the water will be converted into OH minus. And so what we do with this is we combine these two equations. That is, the copper sulfide solid is going to need a water to react with the sulfide that's being generated in this equation. Yeah, and so this is the KSP equation for this. It turns out all sulfides are like this because all sulfides contain sulfide. Sulfide is a powerful base, and it will react with water. So this is KSP double dagger. So that's going to impact our solubility calculations. If we're interested in what is the solubility of CuS in pure water. Okay, so what is the solubility? Then we'd set up an ice equation, but the ice equation we'd set up is not what we call the KSP, it would be KSP double dagger. And so we'll assume, well, this is pure solid, this is pure liquid. We'll assume nothing's dissolved. So this is 0 molar, this is 0 molar. And so whatever dissolves is going to be called S. And so we'll get plus S, plus S, plus S. And so equilibrium will have S molar, and S molar. And so this KSP is just going to equal the copper 2 concentration times the HS minus concentration times the OH minus concentration. The reactants here are solids and liquids, so those all have an activity of 1. So this is just going to equal S cubed. And therefore, the solubility is just equal to the cube root of the KSP double dagger. And so the solubility calculation is a little different because of this complication, additional complication with sulfide. We can change the solubility. We can decrease the solubility. We could decrease the solubility by adding common ion. So, if, for example, we add some copper salt to begin with, or some HS minus, or some OH minus here. If we have common ion here, then the solubility won't be as big, right? But we can also increase the solubility too. The way we can increase the solubility is by changing the pH, because OH minus is base, but we can see the direct impact on this. And so what we're going to do next is we're going to look at something called KSP A double dagger. KSPA double dagger. So if we take our KSP equation for copper sulfide is the sulfide. So for every sulfide, we need water to react with that. So this is going to generate copper 2 plus HS minus plus OH minus. This is our KSP double dagger. Then we can figure out how the acid will impact the solubility. in this case, we want hydronium, so acid. And so what would acid do to this equilibrium? Well, acid's going to attack the strongest base around. What's the strongest base around? OH minus. Yeah, exactly. And so if we remove the hydroxide here, Le Chatelier's principle says it shifts to the right, and so this is going to dramatically increase the pH. We can figure this out quantitatively by doing this here. But once hydroniums attack the hydroxide, there's another base around in here, and that's HS minus. HS minus is, borderline strong. You take a look at the chart over here. Actually, actually, it's not so strong. HS minus is very weak, isn't it? Weaker than water. Not extremely weak. But it's still potentially well, that's as an acid, right? I made a mistake. I shouldn't look at HS minus as an acid. I should look at HS minus as a base. And so we're looking at HS minus as base. It's a moderate base. Not as strong as hydroxide, that would be the next strongest base. And so there's another base present here that could be attacked by acid, and that's hydronium. Hydronium can attack the HS minus, because HS minus is base, so that's going to be influenced by pH. And so this will form H2S and water. H2S and H2 liquid here. And we do something funny here. Something funny is we do it in this chapter, and that is, if I have hydronium and hydroxide, what's the K for that? Well, hydronium is a strong acid, hydroxide is a strong base. So if we have a strong acid, strong base, then we call it very, very, very large. Right? And here we have a strong acid, hydronium, plus a weak base, HS minus. So a strong acid plus a weak base gives us K that is very, very large. And this HS minus is stronger than water, stronger base. And then, and so in this chapter, we have something called the combined method. So the combined method, we're not going to call this one very, very, very large. We're actually going to come out with a number for this. And so if you look at the reverse equation here, if you were to go backwards, what is it? It would just be water plus water yields hydronium and hydroxide. Have you seen water plus water yields hydronium and hydroxide? That's just Kw. And so if we were to look at this reaction going backwards, it's Kw. Reverse it, we've got to invert the K. And so we aren't going to call it very, very, very large, but we know the K value for this. And so the K value for this particular reverse reaction is just 1.0 times 10 to the positive 14 rather than 1.0 times 10 to the negative 14. Well, 1.0 times 10 to the positive 14 doesn't seem so very, very, very large, does it? I mean, that's a number. We can calculate it using our calculator, no problem. And so why didn't we do it before? Why didn't we put the number in before? When we were dealing with chapter 17, why didn't we use the number? Remember when we did those? Step 1, if it's very large or very, very large or very, very, very large, we just did it to completion, right? We didn't actually put a number in there, but we could have. The same thing with this. Take a look at the reverse of this reaction. What is this reaction going backwards? It's going to be the Ka for H2S. Well, the Ka for H2S is known. This is just the Ka equation where H2S plus water yields hydronium and HS minus. The Ka for that is only 1.0 times 10 to the minus 7. And so, we invert it, we get 1.0 times 10 to the positive 7. That's not so very, very large, is it? And so, the question is why am I doing it now? Well, one reason I'm doing it now is because I want to figure out this. If I combine these three equations, I'm going to CuS solid plus 2 hydroniums. This is going to give me Cu2 plus H2S plus 2 waters. Well, one of the reasons I'm combining it now is because I want to figure out what my KSPA double dagger is. My KSPA double dagger is going to be KSP double dagger divided by KW and Ka for H2S. And so I can come up with an actual number for this. I can come up with an actual number for this and then generate the ice table, basically. For this water is pure liquid, copper solids pure solids. Generate an ice table like this. And so the question is why didn't I do this before, you know? Why didn't I just use the number before rather than just assuming it's very large or very, very, very large or whatever, you know? And so what's the answer to that? Well, the reason we didn't do it before is because this very large, very, very, very large, whatever, what that does is it forces us to reset the equilibrium. When we say very large, we're just going to have or assume 100% forward reaction. And then if you look at how we set up the problems before, we just have 100% forward, or whatever, and then we let it equilibrate, because eventually what we'll do is we'll do a step where we regenerate some of the conjugate species, which is actually going in reverse. And so using this very large, very, very large, and very, very, very large is another way of resetting the equilibria. And it's going to be standard for those chapter 17 problems. But in chapter 18, we aren't going to use any of those. We're just going to use the actual numbers and come up with a number. And that's because we could use the combined approach. With the combined approach, what are we doing here? Well, the combined approach works because of this. The combined approach works because of what? Well, actually, since I have a little bit of time, I'll talk about it. Maybe I'm not going to go back and look at some of the other stuff. But why does the combined approach work here? Well, why shouldn't it work for everything? It doesn't work for everything because we're missing species. So for example, if you look at the final equilibrium here, what species are we missing? Hydroxide and hydrogen sulfide ion. The reason why we could ignore those in the final equilibrium is because of this. This first equilibrium has to be very small. So it's very small. It tells us that very little HS minus and very little OH minus is generated. In the next equilibria, then these are very large. And that means whatever HS minus and OH minus is generated, it's immediately attacked, the hydronium. And therefore, the actual concentration of HS minus and OH minus at equilibrium is very small. So small, we're going to call it negligible and completely ignore it. And so the combined approach works when the intermediate species like this are negligible. We couldn't use it for like phosphoric acid, you know, Ka1, Ka2, Ka3 for phosphoric acid, because phosphoric acid, the intermediate species, like dihydrogen phosphate, monohydrogen phosphate, are much more significant in terms of concentration than the final species, which is phosphate. There's very little phosphate in phosphoric acid. If we use the combined approach for phosphoric acid, we get all phosphate. Does that make sense, or do I need to write it down? I need to write it down. I can't combine these. This is Ka1. Ka2. Ka3. So if I were to combine these, I'm going to get 3 phosphoric acid. Oh, no, I'm not going to get 3. I'm going to get a phosphoric acid plus 3 waters yields 3 hydroniums plus a phosphate. What's K for the combined equation? Well, K for the combined equation is just take those 3 Ks, Ka1 times Ka2 times Ka3. Therefore, I do 3 steps, combine them into 1 step. Rather than solving 3 ice tables, now I only have to solve 1 ice table. But the combined approach fails for this because well, right. What's the biggest K? The biggest K is going to be Ka1, and then it gets progressively smaller. And so the biggest population of species will be phosphoric acid and dihydrogen phosphate. And so most of this ends up, you know, whatever reacts, most of it ends up as dihydrogen. And then there's going to be a lot less monohydrogen and a lot less phosphate. But if I look at the combined equilibria, this is assuming that, you know, any phosphoric acid that reacts with water will form phosphate. And so in the combined equilibria, there are only 2 species, phosphoric acid and phosphate. What happened to the dihydrogen phosphate? What happened to the monohydrogen phosphate? Well, they're being ignored. Is it okay to ignore the dihydrogen and monohydrogen? No, that's completely wrong, because phosphate would be the species with the lowest population, you know, compared to something like dihydrogen and phosphoric acid. And so, in other words, we can't ignore the intermediate species, dihydrogen phosphate and monohydrogen phosphate, completely ignore them here because those are significant. Right? Versus over here, we can completely ignore them because we generate very little HS minus, OH minus, and whatever we generate, we consume quite aggressively because these have very large Ks. Does that make sense? Maybe what I was saying earlier about the resetting, does it make sense what I was saying earlier about why we're using numbers here rather than calling this very, very, very large? All right, let me talk about that. Okay, why we use numbers there. Earlier we just used very, very, you know, we used all those. there are two ways to do these particular problems. And so let's say I have something like this. Let's say I have acetic acid plus sodium hydroxide. I'm not going to try to get a number for this. I'm just going to call this, yeah, very, very large. This is going to go to sodium acetate and water. Well, yeah, I mean, how you're going to approach the calculation, but let's just do for any generic. But did I really have to call this very, very large? Look at that reaction carefully and reverse it. What do you see? What do you see? Okay, this is what I see. I see sodium acetate or acetate. Sodium ions are doing acetate plus water. Acetate plus water yields acetic acid plus hydroxide. Acetate plus water yields acetic acid plus hydroxide. That's what equation is that? Maybe I need to come back. Acetate plus water yields acetic acid plus hydroxide. Yeah, I mean, what is this equation called? This is K. This is KB. So we call this K. Remember the K? The K is very, very, very large. But you know, eventually you start seeing enough of these that you go, that doesn't sound right, because I know what the K is, especially after chapter 18. The K is 1 over the KB for acetate. Well, I could actually calculate the number here. No big deal. I could calculate the number. Because the K